Hi, my name is Brian Bailey, and I'm the team leader of the Justice League. Our problem, hard to open and close doors. Our client, Honda Manufacturing of Alabama. Now sit back and relax and enjoy the presentation.
This is Emily Chatterson. The problem that our project is based on is data collection for Honda's hard to open and close doors. Honda recognizes that hard to close doors are one of their top customer complaints, but due to the various factors that impact door closure performance, it has been difficult to get a large quantity of closure data, especially from mass production vehicles. Honda's current method of data collection requires the vehicle to be completely removed from the assembly line. Once in a testing facility, the LMI GWiz device shown on the left is suction cupped to the door. This device is then used in an iterative process where the user closes the door multiple times to narrow down the minimum required velocity to fully latch the door. This method can take quite a few minutes in a laboratory setting, and due to the low amount of data collected, it's not extremely useful in drawing conclusions about mass production vehicles. Due to the time constraint on the assembly line, a different method is used for quality control. The same LMI device is attached to the car doors as they travel down the assembly line. Each car door is then open and closed, and as long as the velocity value shown is under the upper threshold, or about 1.2 meters per second for most models, the vehicle will continue down the line. If the vehicle door is not able to fully latch under the given threshold, the vehicle is removed and sent to be repaired. This eliminates very hard to close doors, but does not actually measure anything, and because of this, there is no useful data being collected, therefore there's nothing to analyze.
Hi, I'm Sean Keenan, and I will be briefly discussing the expected deliverables and the design requirements for our project. So to start off, Honda expects us to be able to deliver a concept and working prototype that can estimate the minimum velocity and energy for closing a car door within 30 seconds. In order to do this, they expect us to develop relationships between the variables that affect the closing of a car door. Honda absolutely requires us to find the minimum speed output for closing a car door, and this has to take less than 30 seconds and be accurate to plus or minus 0.05 meters per second to what the actual value is. We have to have a simple user interface, and we cannot damage the vehicles at all. Honda would like, but doesn't absolutely need, the minimum energy output for closing a car door and for our method to work on other types of doors. In identifying the factors that affect the closing of a car door, we first made a couple of assumptions. The first one being that the door hinge friction is negligible, as it accounts for less than 2% of the total energy calculation. The checker will be ignored as well. To describe what the checker is, right here in that red box is the checker. This image shows the arm that the door rests on as it opens and closes. That checker is in place to keep the door from being slammed too hard. So obviously this has a great effect on the total energy calculation. After this, we came down to three key factors that affect the minimum closing velocity of doors. The first being the weather stripping, then we have the door latch, and the cabin pressure of the car. Just to give you a couple more visuals, outlined in red here is the weather stripping. That's the rubber that lines the door. This, of course, provides resistance to the door actually shutting, as there's a reaction force on the rubber when the door is closed. The top right here, that is the door latch. There's a force required to overcome the door latch, so that needs to be investigated in our project as well.
Hi, it's Brian again. For team organization, the responsibilities of each member are as follows. Team leader is myself. Software and control systems are Peter, Sean, and Emily. Electrical systems are Peter and myself. Mechanical systems are Mason and myself. Data analysis and machine learning is Dylan and Emily. Communications is Emily, and the purchaser is Mason. The flowchart shown here details our approach to the project. After research, our team broke into three groups. Apparatus design and electrical systems were in charge of designing, building, and coding our apparatus. The data analysis team was in charge of understanding and learning machine learning software in order to analyze our data received in the data acquisition phase. Unfortunately, due to the coronavirus outbreak, The data acquisition phase was not completed, and therefore machine learning also was not completed. These were critical factors in our project, and therefore our final deliverable was not met. The table shown here is the Gantt chart for our project. It details the major milestones and the timeline for each of those milestones. Last semester, our focus was researching and understanding the complexity of our problem. This semester was spent designing, building, and coding our apparatus, along with researching machine learning. Data collection was a huge part of our project, but is left incomplete due to world events. Seen here in red are all the major milestones that are left incomplete due to this inconvenience. This slide summarizes the costs associated with our project. The table to the right shows the direct cost to the University of Alabama on behalf of our team. The direct cost totaled to $753. Throughout the semester, donations were required to the estimated total of $234. In total, the cost of our project was $987. Labor costs were kept to zero due to the design of our apparatus and previous experience of our team. We were able to machine and build the apparatus in the student machine shop.
Hi, I'm Mason Kinney, and I will be going over the mechanical overview and some structural analysis and some FEA analysis done on the apparatus in SolidWorks. So the entire supporting frame of the apparatus was constructed out of 80-20 aluminum extrusion. This extrusion has grooves in it which allow the mounting of the linear actuator to be adjustable for height. This is important because we wanted to be able to apply pressure on specific spots on each door, so the height is adjustable in order to be able to accomplish that. There's also a second shelf below the linear actuator which will house and protect all of the electronics required to operate the apparatus. There's also a steel floor plate that is bolted to the aluminum extrusion. This provides a spot for us to add excess weight to prevent any translation or movement of the device during operation, and it also increases the contact patch with the apparatus and the ground. The linear actuator is a custom tool head, and sandwiched in between the custom tool head and the moving rod of the linear actuator is a load cell. This load cell is used to measure the force being applied by the linear actuator. Built into the linear actuator is a potentiometer which allows us to calculate the distance that the rod has traveled. There are also 4 retractable casters that are mounted to each corner of the apparatus. This allows for the entire apparatus to be lifted off the ground and be rolled around the vehicle with extreme ease. So some structural analysis was performed in order to guarantee that the actuator could stand up to the load and not translate while under operation. So some design parameters that were considered was that it was determined that it takes a maximum of 340 newtons to be able to latch a door. We also determined that there is a static coefficient of friction of 0.65 between the steel plate and the concrete floor. The dimensions of the framework were also taken into account. Assumptions of the calculations was that the entire apparatus must maintain static equilibrium. All of the force from being applied to the door is also being applied to the device at point A in the positive X direction. The extra weight put on the steel plate was evenly distributed and centered at point W. We also assumed that all the bolted joints are completely rigid. So after calculations, we determined that in order to prevent tipping of the actuator, we would need an extra 57 kilograms positioned at point W, which is 0.41 meters from the front of the apparatus. With this weight, the frictional force you needed to push the device backwards, so slide across the concrete floor, was 363.3 newtons. Because this is higher than our maximum force applied at point A, which is 340 newtons, we determined that it will not move under normal operation. Some structural analysis done in SolidWorks determined that the von Mises stress for the entire aluminum extrusion frame was strong enough to prevent any deformation. And then we also determined that a minimum factor of safety for the device was 4.42. So the apparatus was determined safe.
Shown here is a flowchart which describes the program behind the actuation and data acquisition process. First, the program is called within a Raspberry Pi using the Python 3 programming language. Libraries are then imported which allow the Raspberry Pi to read data from an analog digital converter along with a load cell amplifier. The load cell is then tarred. The user is then prompted to record the VIN number, which will become the name of the CSV file to be exported later. The user is then prompted to push the start button. When the start button is pushed, the actuation will begin. A CSV file will instantaneously be created and begin recording force and displacement values as read by the Raspberry Pi. This occurs until the Arduino input shifts to a high voltage. This signifies that the Arduino's contact microphone has picked up two distinct latches within the door, stopping the actuation and closing and exporting the CSV file. The program then resets for use on the next car door. The electrical component breakdown begins with the Raspberry Pi 4. The Raspberry Pi is the brains of the whole operation and is where the data will be exported to. The MCP3008 is a 10-bit analog to digital converter responsible for the actuator's onboard displacement potentiometer readings. The SparkFun HX711 is a load cell amplifier and has an onboard 24-bit analog digital converter and is responsible for reading the load cell's force readings. The Allego Uno is an Arduino equivalent which we use to control the piezoelectric contact microphone system. More on that in a bit. The DC motor controller is used to provide power to the actuator. The LRS-120 converts a normal AC signal from a wall outlet to a 12-volt DC signal, which our motor controller needs. Piezoelectric contact microphone, and last but not least, the actuator itself is the FAPO150-1212. Here's the pinout of the Raspberry Pi. Some important things to note here that the ground and the 5-volt are actually connected to the Allego Uno. This is to ensure a common ground so that the Allego Uno can send a high signal to the Raspberry Pi when it detects those two latches. Also noted here, LED indicators indicate different states that the program's in. Here's the sensor wire diagram. This is not the full wire diagram of the Raspberry Pi, but it just contains the sensors. It gets a little busy when all the wires and LEDs are there. But shown here, you can see the actuator's potentiometer on the bottom is actually a part of the linear actuator. It's just shown there as a potentiometer. And that's actually hooked up to the MCP3008 ADC. The HX711 is our load cell amplifier, and there is the button load cell. The actuator wire diagram starts at a standard 120 volt 15 amp AC wall outlet, moves through our DC power supply and onto the motor controller. Those thinner wires that go up to the Raspberry Pi and the MCP3008 are control wires or data collection wires. That's why they're thinner. They're not housing the large amounts of power which are needed comparatively to move the linear actuator. Here's the pinout of our Allego Uno, our Arduino equivalent, which we're using. Again, you can note that the Raspberry Pi 5-volt and the Raspberry Pi ground is connected to the 5-volt and ground of the Allego Uno. This is to ensure a common ground. The piezoelectric contact microphone is pretty simple. It detects vibrations through the surface. It's really sensitive, and it's used to sense those two latches that the door is going to go through before it actually completely shuts.
Hello, Dylan Berdlich here to talk about data acquisition. Velocity and pressure measurements are recorded after each manual closing of the door. This allows the machine learning algorithm to model the behavior of doors with various latching energies and minimum closing velocities. The latching energy is found using force and displacement data from one actuation. The figure on the right depicts a trapezoidal integral approximation, which is one of three summation methods used to approximate the latching energy. The purpose of having three methods is to reduce the bias of the apparatus. Finally, the minimum closing velocity is found using Honda's existing iterative method. All of the mentioned data is compiled into a table on the left, which is used to train the algorithm. As you can see, the velocity and pressure values vary, but the energy and minimum closing velocities are assumed constant for a given door.
One of the machine learning models that is used in this project is a linear regression model. Regression models are used to apply many inputs into a single output value. Three predetermined models that are used in our code are the linear, interactions, and quadratic models. They each are trained the same way with the same vehicle information, but all three have different terms used in the calculations. Because we were unable to measure a full set of training vehicles, or about 30 vehicles, it will be best to test each of these three variations and compare the results to determine which gives the most accurate prediction values.
Hello, Dylan Bertolick here again. Training tables like the one shown in the data acquisition slide are used to train the classification model. These training data points are shown in blue on the graph. These points have known values of minimum closing velocity associated with them and are organized into groups. The model makes predictions for minimum closing velocity based on the Euclidean distance between these training points and the test points shown in red. Prediction accuracy will increase as more training tables are added. The product evaluation method for our project is simple. Knowing the value for minimum closing velocity that the model should predict means we are performing what is known as supervised machine learning. 2 sets of 10 cars each will be used for optimization and validation. The optimization set will be used to improve the accuracy of the model's predictions, and the validation set will be used to ensure the model accurately predicts values for cars not used in its training. If the model is more accurate at predicting values for the optimization set than the validation set, overfitting has occurred. Preliminary results are promising. Using fake data created based on the training data, 21 out of 24 tested points were predicted to within 0.05 meters per second of their true values. The team that continues this project will be able to refine the approach in the following ways. First, they could improve the repeatability of data acquisition. Mechanisms to open the door to a set angle and shut them at various velocities would eliminate the human element and reduce deviation from the linear velocity-pressure relationship. Second, they should conduct research into model parameters that affect prediction accuracy. This way, the codes can be adjusted should new trends appear. Next, the accuracy of all the models created should be compared. This will also give a conclusion as to which energy summation method produces the most accurate results. Finally, the group should train the existing models using latching energy as the only predictor variable. If these models are as accurate in their predictions as the ones incorporating velocity and pressure are unnecessary. This knowledge will greatly reduce the effort necessary to create predictive models for other car types.
There are many positive potential impacts of implementing our technology onto a production line. First and foremost, it can be almost entirely automated. This accelerates and makes the quality control process more accurate. Taking out humans from the line lowers the cost of quality control as well. Since our technology takes data from every single car, it can give manufacturers a key advantage to troubleshooting problems. These large data sets can even allow for early detection of problems before anyone notices that there's a quality issue beginning to develop.